Hello, this is Jason Guest for Team 15, midterm presentation. About a month into my project, I took a task for the software-based implementation of our project. Our project was split up into 3 implementations, and the software was supposed to be the baseline, which kind of showed, what we could expect for performance out of the other ones. The other ones were designed to be faster, but the software one was our baseline, so we wanted it to be really good. And I took a task to kind of formalize and get it structured so we could build up upon it later and get a lot of results from it. And it was designed so that we could take input from our quadrature decoder, which is like a really accurate and more signal output potentiometer, and send the data to our Mega 4809 microcontroller and decode those signals and output it on USART. So the problem I was running into was that after I had it all plugged in, I had the firmware written, and I had it flashed to the device, the board's onboard LED was flashing for low power, so the board wasn't getting enough power to do what I wanted to do. And not only that, it wasn't sending the correct USART signals to the computer, and our LED array is supposed to be kind of incremented based on the way I was turning the device, really wasn't doing what it was supposed to. It was flashing dim and just wasn't giving me the right patterns. So I was dumbfounded. I thought, there's no way I could be having these kind of issues. It's so simple of an application. And so I started testing things. Well, the only thing I had really plugged in that was taking power from the board was the LEDs and the encoder. So I took out the encoder just to see if it would still run afterwards if I had a problem with the board. And I found that the decoder was really the reason that I was having these power issues. And I continued testing. I plugged the decoder back in, and I designed a set of test cases where I spun it really fast to see what would happen. I spun it really slow, and I just did a normal turn. So I developed my maximum edge case, my minimum edge case, and my common case. And I found that I was getting high power consumption because when I'm turning it, it sends a lot of signals based on every tick of rotation, and the software-based implementation just couldn't keep up, and it was trying to calculate which way it was turning, how fast is it turning. It was trying to increment the state counter, and it was also trying to send a bunch of messages to USART. So my solution was my choices were to either somehow limit what I was going to be able to decode, or I needed to add an external power source. Obviously, we couldn't limit it. We wanted this to be really accurate and a good performance baseline for the other implementations, which were going to be faster. So I had to find a way to get power into the breadboard, outside of what I was already getting from this USB cable. And I was actually using a 6-pin USART cable, like a serial cable, to the other side of my computer via another USB port to send the messages. And I thought, well, why not just use that? Because I can't really put a battery on there onto the board, or I might fry this new hardware that I just got, and I really didn't want to be that guy. So I plugged it in, and I started running tests, and it worked great. I found that I was able to power just the encoder with the USART cable, and I was able to power the board separately with the USB cable to the computer, and they didn't run into any issues. So the board only had to focus on running the calculations and decoding the input from the decoder, and updating the LED and sending messages to USART. And through that, I was actually able to also find out that the USART message errors were coming from my own personal coding errors. And then once I fixed that, I plugged everything back in again, and it worked as I wanted it to, and we were able to use that for other implementations and testing the later code as we went on in the semester. And so I was able to learn a lot from that specific issue, and I'm glad I ran into it early on. Professor Sandy always says 30% code, 70% debug. It couldn't be more right. For future projects, and definitely as I keep going with this capstone before we end, definitely going to give myself less time to just write the task, finish it out really quick, give myself time to fail, find a solution and keep failing, and just keep doing it over and over and over again until I somehow find my solution. Also, a big source of the problem for this specific issue I ran into was that I was really unfamiliar with the hardware I was using. I didn't know how much voltage each of the pieces was going to require, if it was going to consume a lot of power as I used it, and that really just taught me the importance of data sheets and going to data sheets, reading your data sheets, and not only that, with taking that information you get from data sheets and forming the correct kind of test cases, you know, finding your maximum edge cases, your minimum edge cases, finding your common case, and defining a set of test cases so that you're left with no errors or no uncertainty in what the source of the issue is and how to fix it. So for future problems, I was able to, you know, take this what I learned from this issue and design myself a set of test cases and just a method, a foolproof method, and how I can go about resolving issues when they come up. And you know, because of what I learned in this initial problem, I really haven't run into any other big issues as capstone went on. And so yeah, that was my problem. You know, how I went about solving it and the solution.